Hello, and welcome back to Shiksha Costa. Today we're going to do a review on the unit connecting graphs and equations of quadratic functions. So in this unit, we learned that we were able to demonstrate that we understand what a function is, and also we learned how to make connections between the numbers, the graphs, and the algebra for quadratic functions. As part of this specifically, you should have been able to, by now, explain the meaning of the term function, be able to substitute in and evaluate linear and quadratic functions that are given in function notation, explain what the domain and range of a function are, and actually find out what those are for any given quadratic function. Determine what does a, h, and k do in the vertex form of a quadratic function, and describe them in terms of how do they transform the base function x squared. And then using that, you should be able to sketch the graph of y equals of the quadratic form of the vertex form of a quadratic function. Finally, you should be able to go between the standard, vertex, and factored forms of a quadratic and describe all the information that you can get from any of these and use that to help you sketch the graph of a quadratic. When we started this unit, we first saw that sometimes two or more relations actually create the same graph, and that means all of their x and y values are identical. For any value of x, the value of y is the same, and we call these equivalent relations. In this unit, we looked at the vertex, factored, and standard form of a quadratic, and in this example, all three of these generate the exact same graph. They are all equivalent. And we also, by the end of this unit, we learned that we can even predict what points are going to appear on the graph just by looking at the numbers that show up in here. We learned function notation first, and we learned that a symbol like this, we call this f at x. This is function notation, and this tells you the value of the dependent variable, which we usually label y, for a given value of the independent variable. And what that just means is it's a very long-winded way of saying instead of saying y, we'll start saying f at x, or g at x if that's a different function, or c at t if it's the cost for a certain amount of time and we just change the variables around. Like I mentioned, we read this as f at x, and that's better than using y because we can say stuff like, hey, what's f at 2? That's a very quick way of saying the y coordinate of the function when x equals 2. What is a function? It's a way to connect one input to one output. And we can express a function like, a set of ordered pairs. We can use a mapping diagram to show you for these inputs, what is the output that it leads to. We can create an equation to tell you what the output should be. We can map those inputs and outputs connections on a graph or even on a table of values. For something to be a function, if there is an x value that appears more than once, though they should all lead to the exact same y value. So each unique input should never lead to more than one output, just like it says over here. If that's on a graph, that means that it should be able to pass something called a vertical line test, where you just put a vertical line down, and if it touches the graph at 2 points, it's not a function. All of the inputs that are acceptable collectively are called the domain of a function, and all of the outputs that you could achieve are called the range. To express domain and range, you start with putting a D or R, and you express it in set notation, so you use curly brackets. First, you specify the variable or the function that represents all of these values. You put a straight line to separate a rule that's going to appear. You might place a restriction on what this variable could be. For example, maybe it has to be greater than or equal to 0, or maybe between two values. You put another line to show that you're going to input another rule, and then you specify the number set that the variable or the function belongs to, the set that it is an element of. When you are deciding on the domain or range of a function, remember that if you're working with a real-world problem, you have to use this portion right here to restrict the domain and range according to what the situation calls for. From there, we learned about how to transform quadratic functions. So if you do see a number in front of the x squared, if you do see that the equation has an a value, that stretches or compresses the function vertically. If that's going to be a number that's bigger than 1 or less than -1, there's always going to be a vertical stretch. In other words, when we multiply by a number that's bigger than 1, obviously the value that we are multiplying gets bigger. But if it's negative, so if it's less than -1, not only is there going to be a vertical stretch, but it's also going to be reflected vertically. When it's a small number, for example, between 0 and 1 or 0 and -1, that compresses the function vertically. Like when you multiply a number by something that's less than 1, the number will, of course, get smaller. And just like a stretch, if that number is a negative number between 0 and -1, for example, it's also going to be reflected across the x-axis. Then we learned what do h and k do. H and k, the graph of y equals x minus h squared plus k, is exactly the same as y equals x squared. It's just translated or shifted or slid up, down, left, or right. When h is a number that's greater than 0, when it's positive, that moves the function towards the right. It's a translation right. If it's negative, it translates it left. Similarly for k, if k is positive, if it's more than 0, it translates up, or if it's less than 0, it translates down. Putting all of that together, compared with the graph y equals x squared, the vertex form of a function is still a parabola, but it's been stretched or compressed vertically by a factor of a. It's been translated horizontally by h, and it's been translated vertically by k. And finally, if a is a negative number, it's also been reflected vertically, or in the x-axis. The vertex of a parabola, this is called vertex form because it's really easy to pull the vertex of the parabola from the equation. Just look at these two numbers, h and k. The axis of symmetry is a vertical line that creates sort of like a mirror of the parabola, and its equation is x equals whatever this number is, h. When you are transcribing a point from x squared to find its new location on this graph, there is a certain order of operations that you have to follow. So if this point appears on y equals x squared, its new location on this equation is going to be, you take the x value and you add h, you take the y value and you multiply it by a and then add k, and this is going to be the image or the new location of this point. And any point on the original graph can be translated or transformed to find its new location just by using these two formulas. For example, if we wanted to sketch the graph and we didn't want to use any transformations, actually, this is a really basic parabola. And one thing I know is that the vertex, which is at 0, 0, is now going to be at 4 and 10. So I can plot that point right there. And then if I choose an x value that's near here, so this is the x value 4, I could choose 5 or 3 or 6 or 2. I'm going to choose 6 because it's pretty close, but it's not, super, super close. I'm trying to find something that's kind of far away to plot another point. If I choose the value 6 and I plug it in, if I find out what is f at 6, I'll find that's -2, which means I can put a point right over here. And knowing what I know about the axis of symmetry, which is x equals h or x equals 4, that would be a line going right there. What this symmetry means is that there is another point. This is like a mirror, and there's another point on the other side of the mirror exactly the same distance. This is 2 units away here. So 2 units away on this side, at the same height, there will be another point. And then now that I have 3 points, I can just connect them with a nice smooth curve, and there's my parabola. In the last portion of this unit, we learned how to go between the different forms of a quadratic. For example, vertex and standard form, these two equations represent the exact same parabola, but how do we go from one to the other? If you're given an equation in vertex form, it's really easy to turn it to standard form. Just expand and simplify. Just turn the brackets, use FOIL and all that jazz and collect your like terms, and you've got standard form. Going from standard form to vertex form is a lot more complicated. In this case, we have to do that process called completing the square, which means factoring out the a value out of the first two terms and going through a whole bunch more steps to create a perfect square trinomial, which factors into x plus a squared. Finally, we learned how to graph quadratics from their various forms. We already saw how to graph them from vertex form, but what about factored form? Factored form is quite easy. You just graph the x-intercepts first. You find the value that's right in between by averaging these two, and that's the axis of symmetry's value. And we know that line goes through the vertex, so we can just take that and plug it into the function, and that will give us the maximum or minimum value. That's the y-coordinate of the vertex. You can plot that point, and boom, you've got 3 points that you can connect with a nice smooth curve. One recommendation I would definitely make is try to do all the calculations of these values first so that you can actually draw your scale in a nice, neat way so that it includes all of those numbers. All three forms of a quadratic give you information about some points on the graph. Standard form tells you about the y-intercept because that's just that number at the end. To go to vertex form, we can complete the square, and then the vertex can be found just by looking at h and k. If we wanted to go from vertex to standard, we just expand and simplify, and then we can factor it to get into factored form. And factored form tells us the two roots are r and s. If we wanted to go back to standard form from there, we can again just expand and simplify. These are four really important points that can tell you a lot about how to graph that quadratic. And the more points you have, the more accurate and the easier your sketch will be. Just keep in mind that not every quadratic relation has a factored form. So not everything will actually be factorable. And some quadratics don't even have any zeros or any real zeros. Let's do an example of sketching this quadratic. So right away, this is in standard form, so I know that I can pull the y-intercept. It's going to be 8, and I can plot that point right over there. From here, I can factor this expression, and x squared plus 6x plus 8. I'm just looking for two factors of 8 that add up to 6. 1 and 8 aren't going to do it, but 4 and 2 will. 4 plus 2 is 6. So this will just factor into x plus 4, x plus 2, which means the zeros are -4 and -2, and I can plot those right over here. Finally, I'll have to complete the square, which means I'll take this value divided by 2 and square it to get 9. And this is the number I needed this to be in order for this to be a perfect square trinomial. Unfortunately, it's not that. Instead, what I can do is I can add and subtract 9. Basically, I've added 0. And now these first three values factor quite easily into x plus 3 squared. And these last two values can be combined into -1. And that tells me that the vertex is just going to be at -3, -1, which I can plot right there. And finally, now that I have 4 nice points, I can connect them all with a smooth curve. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.